Let's look at an explosion in 2 dimensions. We have a black object right here, which will explode into 3 pieces, blue, red, and green. We want to determine the momentum of the third piece right here, given the momentum of piece 1 and piece 2. Can you see why the third piece moves the way it is shown? Now earlier we talked briefly about how if you have 3 or more objects colliding, it's almost impossible to predict what happens, and now here we have 3 pieces. Well, the difference is we're telling you the initial momentum is 0, giving the values of P2 and P1, and we're only asking for P3, so that's okay. So let's get back here. Why is the third piece moving in that direction? During an explosion, the total momentum is unchanged. There are no external forces acting on the system. We do have the potential energy of this box changing into kinetic energy, but that's internal to our system. By Newton's third law, the forces that occur between the particles within the object will add up to 0, so they don't affect the momentum. If the initial momentum is 0, which it is, the final momentum has to be 0. So the third piece of this must have equal and opposite momentum to the sum of the other 2 pieces. So that's what's sketched in here. Here's the momentum of P'1 after the explosion, and here's an equal and opposite right down there. Here's the momentum of P2 after the explosion. Here's its equal and opposite component. So when I add these 2 vectorially, I get P3' moving off in this direction. We have the initial momentum of this object in the center is 0. So Px has to equal Py, which equals 0. It then explodes, and we know the momentum of P'2 and P'1. P'1 is only in the x direction, so right over here it shows that its y direction is 0. P2' has no momentum in the x direction, so that's equal to 0. Now let's come on over here. After the explosion, momentum is conserved in the x direction, also in the y direction. So I take my term here where P'1y equals 0, look right here, and this term cancels out, and then I come up over, just follow the line, and I have P'3y is negative P'2y. I'm going to do a similar thing for the x direction. I have P' of 2x is equal to 0, so this term goes out. Then I come on over and I find that P' of 3x is going to be negative P' of 1x. So now I can substitute my values in for P'3. That's just P'3x quantity squared plus P'3y, the quantity squared, take the square root. I make these substitutions here, right, because I don't know what these guys are, and I have P'1x quantity squared and P'2y quantity squared. Again, we don't worry about the negative signs, they're going to cancel out. Here's the only tricky part. You're used to tangent being y over x. Then how come I have x over y in this case? Well, you have to go back to the sketch. That's why it's so important to draw sketches. In this case, I'm trying to find this angle theta relative to the negative y direction. I could also have asked you to find this theta, but here we're finding this one. So when I take the arc tan, this side, the opposite side, happens to be P'2x. So that's why you have the x there. The adjacent is in the y direction. So the subscripts are a little different than what you're used to, and I did that on purpose. The whole idea is for math to serve physics and not the other way around.